Hello my dear students, let us take one more example on I section. Okay, a rolled I section of size 50 mm by 75 mm is used as a beam, simply supported beam with an effective span of 3 meter. The flanges are 5 mm thick and web is 3.75 mm thick. Calculate the uniformly distributed load the beam can carry if the maximum intensity of shear stress induced is limited to 40 Newton per millimeter square. Okay, this is the question paper problem. So what you have to calculate here, also you have to calculate W. Okay, it is a simply supported beam and the uniformly distributed load you have to calculate. W you have to calculate, but here it is limited to shear stress is limited to 40 Newton per millimeter square. So you have to use only shear stress equation. See, how to calculate this shear stress equation means I have told while explaining the theory, in case of I section and if the maximum shear stress will be induced at the neutral axis. So, you have to calculate shear stress at the neutral axis. Okay, for that you have to use the formula shear stress tau is equal to F into AY bar divided by I into B. Okay, for this we required F, I, B, A, Y bar. Okay, one by one we will calculate. This is a symmetrical I section 50 mm. This is 50 mm and 75 mm is overall depth is 75 mm. And flange, this is given that effective thick. Flanges are 5 mm thick, so that is flange thickness 5 mm and web is 3.75 mm. That is web thickness is 3.75 mm. Now neutral axis is, this is a symmetrical I section, so neutral axis is exactly at the center. So 75 divided by 2, that is 37.5. So the neutral axis lies at a distance of 37.5 meter from the top and also the bottom layer. Okay, let us mark this as the neutral axis. Okay, this is neutral axis. Now position of the neutral axis. Okay, now what you have to calculate? You have to calculate I. How I can calculate I? In the case of symmetrical section, I is given by BD cube divided by 12 minus small bd cube divided by 12. What is capital B here? This is capital B 50 mm and capital D is 75 mm. Small b is 50 minus 3.75, that is small b 46.25, and small d is overall depth is 75 minus 5 minus 5. So 75 minus 10, that is equal to 65. Okay, this is small d. So now we have capital B is 50, small b is 46.25, capital D is 75, small d is 65. So now you can calculate what is I. Substitute in this equation. B is equal to 50 and D is capital D is 75 cube divided by 12 minus small b. Small b is 46.25 into small d is 65 cube divided by 12. You get this answer 69.36 into 10 raised to 3 millimeter raised to 4. Now I you have calculated. Next step, what you have to, we have that formula, that is maximum shear stress at the neutral axis. Why at the neutral axis? Because shear stress induced is maximum shear stress induced is at the neutral axis. So tau maximum is equal to F into I into B divided F divided by IB into AY bar. Here, what is F? F is shear force. Shear force for simply supported beam, F is equal to WL by 2. Okay, so F is equal to WL by 2. But because this is simply supported beam with the UDL, F is equal to WL by 2. Now, I already calculated. B is width of the web, because neutral axis lies passes through the web. So width of the web you have to consider, that is 3.75 mm. This is neutral axis is here, so you have to consider this width, that is 3.75. Now, F we know, I we know, B we know. What is this AY bar? See this definition properly. You have to remember always this. What is y bar, that is moment of flange area about neutral axis plus moment of web area above the neutral axis, means what you have to consider, this is the neutral axis position, so you have to consider this portion. Okay, so what it is saying, moment of flange area about neutral axis. Moment of flange area about neutral axis means this portion, and moment of web area above the neutral axis, because we are considering only this portion, so you have to consider only this portion. So moment of area of web area above the neutral axis, about the neutral axis. That is the definition for a y bar. Now we will see what is that. Moment of flange area about neutral axis. What is flange area here? 50 into 5, that is flange area. This we are considering above the neutral axis. 50 into 5, that is flange area, into we are considering moment of flange area. So what is that? About the neutral axis. So from this to here, this distance we have to calculate. Here to here, a y bar means y bar you are calculate. What is this portion? What is that? See, this is 37.5. We want this distance, that is 37.5 minus this is 5. Okay, total this is 5, so this is 2.5. Okay, so 37.5 minus 5 divided by 2. 37.5 minus 5 by 2. Or you can consider this also. This distance total is this 37.5 from here to here, that is 32.5. From here to here, this distance is 37.5 minus 5, that is equal to 32.5. So what is y? We want here to here, that is 32.5 plus 5 divided by 2. Anything, any way you can calculate, either 32.5 plus 5 divided by 2 or 37.5 minus 5 divided by 2. Plus, now moment of web area above the neutral axis. What is moment of web area above the neutral axis? Only this portion. What is that? 32.5 into 3.75. So 3.75 into 32.5. Now y bar you have to calculate for that. What is y bar? It is somewhere here. Okay, neutral axis CG of this lies somewhere here. That distance you have to consider. What is that? That is here it is 32.5. So 32.5 divided by 2. That is this distance. Okay, so this is for the first one, y bar for first section flange. This is y2 for the second portion. Okay, that is from here to here, that is 32.5 divided by 2. CG lies here, so that is the meaning. So that is equal to a y bar. So just remember this formula. Moment of flange area about the neutral axis plus moment of web area above the neutral axis, because web area below also there is a web area, but we are considering above that. So above the web area you have to consider only that portion, that is 3.75 to 32.5 into y bar. Y bar is distance from CG to the neutral axis, that is 32.5 divided by 2. You get a y bar is equal to 10730.47 mm cube. Why mm cube? Area is mm square and y bar is mm, so that is mm cube. Now we have all the values. We can use this equation. Maximum shear stress at the neutral axis, that is tau maximum is equal to F into IB divided by a y bar. So what is tau maximum? It is given here in this formula problem, that is 40. So substitute that equal to 40 equal to F. Let it be F like that only. Afterwards you can substitute what is F. F divided by I. I is 699.36 into 10 raised to 3 into B, width of the web, that is 3.75 into a y bar. A y bar is this value. Okay, write this AY bar. So you get F is equal to 977.627 Newton. But we want the W. We know for the simply supported beam with the UDL, F is equal to WL divided by 2. So substitute W is equal to 2 into F divided by L. So 2 into F is 9776.27 divided by L. L is equal to length is 3000 millimeter, or you can write in meters also, no problem. Then you get the answer in Newton per meter. So this is 6517.5 Newton per meter, or 6.52 kilonewton per meter. Okay, so like this you can calculate what is intensity of the load when the I section is given. Okay, only main thing, it is very simple. You should remember this formula. For that, all the terms you should know. Mainly F, it is always you should know that for the different beams, for the different loading condition, what is F. If you know that, you can calculate what is F. And I, that is for I section, capital BD cube divided by 12 minus small BD cube divided by 12, and B is width of the web. Then AY bar, this definition you remember, that is very important. So only above the neutral axis portion you have to consider. So AY bar you are considering for the separately, then you are combining here. Okay, so once if you get that, you can substitute in this equation, you will get what is W. I hope all of you understood. If you have any difficulties, we can discuss in the class. Thank you.